Everyone, it's 1 p.m. Eastern Time, and we're having our regular webinar on sulfur colloquium. Today, we have Dr. Stuart Bale, who is a professor of physics at the University of California, Berkeley. He earned a PhD in physics from Did I start recording? Okay. Sorry about that. He got his early PhD physics from University of Minnesota in 1994, doing ionospheric sounding rocket experiments with injected electron beams. After a postdoc in London at Queen Mary College, he arrived at Berkeley at 1997. He is interested in measurements of plasma physics processes that are important in solar and heliospheric physics, currently especially solar wind heating and energization. He is NASA PI on instruments on Parker Solar Probe, Stereo, and WIND spacecraft, and is former director of the Space Science Lab at Berkeley. And today we'll have his talk, The Discrete Structure of Solar Wind Sources, Galvanic Switchbacks, and Hot, Fast Plasma Emerging from Supergranular Boundaries. So please go ahead. I will tell you 5 minutes before the end 45-minute slot.
Okay, thanks, Gregory, and thanks everyone for tuning in. And maybe some of you have heard this before, but I think it's getting more and more interesting. So I hope there's something new here for everyone. What I'll do is see if I can make this work. What I'll do is give you a little very brief overview of Parker Solar Probe. I think people are all pretty much up to speed on the mission by now. And then I'll have a little short review of switchbacks, of Alfvénic switchbacks, which I think are one of the big surprises and potentially one of the important diagnostics that we have from Parker Solar Probe. Then a case study, which is in a paper that was just accepted by AppJ, showing that switchbacks are associated with hotter, faster plasma, almost fast wind-like plasma, I would say, and that is organized by the angular scales of supergranulation, suggesting that the magnetic network is at play in solar wind heating and acceleration. And then I'll show you some data from Encounter 9, which was just a month and a half, 2 months ago, which suggests the same thing. And it seems like it's getting more and more, the phenomena is becoming more and more pronounced. Okay, so to remind you, Parker Solar Probe has 3 major science objectives. The first one is to trace the flow and energy that heats and accelerates the wind. Second one is to understand the origin of the wind, the structure and dynamics of the plasma and magnetic fields at the sources. And the third one is to explore particle acceleration, SEP acceleration. There was a dust objective, which was crossed off after selection, but we have actually made quite substantial progress on dust as well. Okay, the Parker Solar Probe is a spacecraft. It's a not very big spacecraft. I could almost put my arms around it if I were standing next to it, with a big heat shield. My cursor here, a big heat shield on the top of it, some radiators. Spacecraft itself is below. These are pictures from the clean room, and I think this was in Titusville, Florida, at Goddard in a vacuum chamber, and then being integrated into the fairing of the Delta IV Heavy in Florida. The data that I'll talk about here is primarily from the Fields and Sweep instruments. Fields is the instrument that measures electric and magnetic fields. So we have a couple of Fluxgate magnetometers in the back here on a boom that's in shadow behind the heat shield at perihelion. We have a search coil and induction coil magnetometer at the end of the boom. We have a voltage sensor on the boom. And then we have these 2 dipoles, or 4 antennas, are organized into 2 collinear pairs, nearly orthogonal collinear pairs in the plane of the heat shield. The sweep investigation is, so I lead the Fields investigation. Sweep investigation is led by Justin Casper, and is comprised of a Faraday cup, which is mounted up here. So this is an instrument to measure the current of the solar wind, looking directly into the direction of the sun. And then 2 electrostatic analyzers called SPAN A and SPAN B. And this instrument measures electrons and ions, and this one measures only electrons. And they're kind of traditional electrostatic analyzers with the time of flight stage in here. So we have good separation of protons and alphas, which is an important point. I'll also show some data from the ESIS instrument, which is led by Dave McComas. ESIS is a energetic particle instrument that has, you know, from 30 keV up to several MeV particle in principle species separation mass resolution. Okay, so this will come up later. I like to show these plots because at the very end there's some information in this stuff. These are the there are families of orbits, right, where the mission is driven to lower and lower altitudes by Venus encounters, Venus gravity assists, and so we have a set of orbits that look alike, and then a Venus gravity assist, and then another set that look alike, etc. The first set of orbits were at 35 solar radii. That's orbits 1, 2, 3, and in Carrington coordinates. So this is in a Carrington frame that's organized by the solar rotation, right? The orbits look like this. So you come in from outside, and then you have a time when you're co-rotational, when you're essentially, which is the green interval here, where you're rotating with the sun. So the wind is in principle coming directly out toward you, and you're driving in radially toward the sun. And then there's a prograde portion of the orbit, perihelion, and then the reverse on the outbound. This is encounter 4 and 5 were like this. They were down to 28 solar radii. Encounters 6 and 7 down to 20 solar radii like this. And in fact, the data I'll show you today, most of the data I'll show you today is from encounter 6. So it has this kind of a organization in Carrington coordinates. And you see that the interesting thing here is that the sweep in longitude is getting to be quite large, right? In the first pass, it's a brief little sweep in longitude, but here it's getting to be quite large. As we go to the next set of encounters, 7, 8 and 9 are similar. We've just gone through 9, and 10 is coming up in a month's time or so at 13 solar radii. You know, it's really 90 degrees in longitude in Carrington longitude that we're sweeping out. So we're essentially driving, you know, across stream structure as we go through perihelion, which turns out to be very interesting, I think. Okay, so what have we seen? Encounter 1, this is old news now, right? This stuff is in Nature. There's an AppJ, a special issue as well, and some ANA papers. But I think two of the striking things that we saw on Encounter 1, the very first perihelion encounter, which was at 35.7 solar radii, two of the striking things were the prevalence of these switchbacks. So this is the radial magnetic field in the top panel, and the red dotted line is 1 over r squared. So it's what you would expect just from simple radial flux expansion of the magnetic field. And so you might have expected that we would see something like in the second panel, just a simple radial field, maybe with some fluctuations, some alphanic turbulence on it, etc. But what we do see instead are these, you know, order 1 radial fluctuations in the magnetic field. So the field is you know, through this entire encounter, you know, this is the field with the switchbacks removed. Through this entire encounter, we're in the negative polarity. We're a little bit south of the ecliptic, you know, below the heliospheric current sheet. We see a negative polarity field, and on top of that negative polarity field are these large, you know, delta B over B1 fluctuations of the field, which is striking. It's not entirely original. These switchback structures have been seen at 1AU. Jack Gosling reported things at 1AU over the poles with Ulysses. Andre Ballard had a paper. Lorenzo Mattiini has published on this. And with Helios, Tim Horbury and his group reanalyzing the Helios data have also shown switchbacks in the inner heliosphere. But what's really striking here is how prevalent they are. And another thing, which I'll get to later, which is that they occur in patches. They're not continuous. There are patches of switchbacks and then quiet radial field intervals, patches of switchbacks, etc. Another interesting thing, I think, from Encounter 1, which I'm going to tell you at the end, we might see again in Encounter 10, is that we basically had perihelion over a small equatorial coronal hole, and really almost every magnetic field model that you could use connected us back magnetically to that coronal hole. So it was also, Encounter 1 was also clear evidence of the role of small equatorial coronal holes in open magnetic field flux. So what are switchbacks? Switchbacks they're Alfvén waves, I think. but they're Alfvén waves with particular structure. So they're generally largely Alfvénic. This is a figure from a paper by Jim Drake showing the magnitude of the field in black on the top here, the radial field in red, and then the two transverse components in green and blue. And so what you see is that you have a mostly incompressible, not entirely, but mostly incompressible magnetic field fluctuation. The radial field abruptly changes direction. Here it goes essentially to zero, but often it goes to fully opposite polarity and back. And then you'll see here, this is the velocity, the radial velocity, and the components, the tangential components of the velocity. You'll see that there's an outward bump in the radial velocity as well, which is sometimes in the Helios literature was sometimes called a jet, not a jet in the sense of a jet originating from it was like a spicule or something, but and we'll come back to that as well. That velocity bump is a feature of the fact that the wave is an incompressible Alfvén wave.
Could you clarify again what is the black curve?
The black curve is the magnitude of the magnetic field.
I see.
And these are the components. Red is radial, and blue and green are the normal and transverse component, the tangential component. And same for below. There's no magnitude here, but these are the components of the velocity. The switchbacks occur on a wide variety of timescales from hours down to fractions of a second. There's an interesting paper that I don't have it called out here in particular, but there's an interesting paper by Thierry de Doctevit showing that there's essentially a power law distribution of deflection timescales in the switchbacks. The switchbacks they're folds of the magnetic field. They're not polarity reversals in the sense of like a current sheet. So I think they're best represented by the cartoon in the bottom left here, which is from a paper by Andrew McNeil. The field essentially bends around and then bends back, and we know that now by looking at the strahl, at the electron, the heat flux coming away from the sun, which maintains its sense in the sense of a fold, and the cross helicity as well of the turbulence. So that's essentially the Alfvén wave Poynting flux is consistent with this sense of a fold. And it's important, actually, I don't have a slide on this. I should have had one, but it's important to note that the velocity impulse that's seen in the switchback occurs coincident with the radial field reversal. Okay, it does not occur at the inflection point here, which is what you might expect if it were a jet. If you had an independent jet of plasma that was dragging the field, like draping the field on its outward flow, then the velocity jet would be displaced from the radial deflection of the field. So we think that this is not a flow in that sense. It's really just an Alfvénic, a large amplitude Alfvén wave that has rotated over. Patches and occurrence. So I think this is one of the more interesting and important things, and that is that these things are not fully ubiquitous. You're kind of guaranteed to see them now on the solar probe encounters, but they are separated. So this is an example. This is from our first paper. So down here are switchbacks. I errantly call these things jets here, but these are switchbacks. And then there's an interval here of just quiet radial field where the field is just simple and radial. The fluctuations, the transverse fluctuations here are Alfvén waves. They're Alfvénic for sure, but the radial field is steady and it's quiet. And you see this is the field magnitude up here. It's generally incompressible. What we have is essentially what looks like a simple quiet flow with a radial field in it. And then intermittently, we have these patches of switchbacks. So they occur, abundantly within the patch, and then there'll be a kind of a quiet interval again. Okay, so this is one of the clues here, I think. Within the patches of switchbacks, this is from a paper by Lloyd Woodham, who's a postdoc at Imperial College in London. So what Lloyd did was look very carefully at the proton temperature, the perpendicular and parallel proton temperature in and around switchbacks. And what he found was that the perpendicular temperature is strongly correlated with the radial flow velocity with this simple, rate solar wind speed. And this this is this is actually fine tuning of that relationship that's well known at 1AU, that the proton temperature and the wind speed are well correlated. Okay, in fact, it's not fully the proton temperature, it's the perpendicular proton temperature. We see that now in the internuclear sphere, which is maybe some indication of a mirror force at work or something. I won't go into that anymore. But interestingly, the parallel proton temperature is well correlated to the patches, not necessarily to individual switchbacks per se, but to, you know, within a patch of switchbacks. So what you're seeing here in this bottom panel is, this is, you know, essentially what we would call a patch of switchbacks, and these are quiet radial field at the edges, and the lower curve here is the parallel proton temperature, which rises and is enhanced within the patch and then goes back out. Generally, the parallel temperature is less than the perpendicular temperature, and I'll come back to that. There's an anisotropy in the proton temperature in the sense that T perp is greater than T parallel. We'll go ahead on the next slide. Okay, switchbacks are largely spherically arc polarized. Okay, so they're Alfvén waves in which the tip of the magnetic field vector is constrained to lie on a sphere. Okay, so the field magnitude is constant. It's, you know, largely incompressible, and the magnetic field, the total magnetic field vector, lies on the tip of a sphere. And so this is what gives rise to this sort of jetting behavior. There's this nice figure in the lower left here from a paper by Lorenzo Mattini. So you see, if you have, which is a good one to look at here, you know, think of, you know, this as being the blue vector here in the lower left figure as being B naught. You know, actually, let's look at this one because this is better. Here's B naught is the blue vector, and now you grow an Alfvén wave on top of that, right? So there's a perpendicular magnetic field component, and so that forces the total field vector to move in this direction, right? So the total field vector is now over here. So you're approaching in this picture, you're approaching a perpendicular switchback essentially, and then in the sense of an Alfvén wave, the radial flow is the vector is in this direction, and so there's a delta VR associated with this in this direction, and that's the thing that we have maybe as a misnomer called a jet associated with an Alfvén wave, but it's basically just the velocity perturbation of the Alfvénic fluctuation in this constrained sense that the magnetic field magnitude is constrained. It's an Alfvén wave, and then I won't get into this too much, but if you fold in the fact that if you fold in WKB, so conservation of wave action, and the expansion, the fact that the wind is expanding, and so the total field magnitude is falling off like 1 over r squared, all those things together can conspire to give you a magnetic field that changes direction as it expands. It's maybe not the only explanation for it, but it's I think a viable one. Because of this jetting, the figure on the right is interesting. This is from a paper by Tim Horbury using Helios data. You know, Tim and his team went through and reanalyzed all the Helios data to maximize the time resolution. And here's an example of a switchback from Helios. So this is a big switchback in fast wind, right? So the bulk flow speed here is 700 kilometers per second or so, and here you see what is the Alfvénic component of the switchback reaching 1,000 kilometers per second or so. So if you look at these things in terms of Poynting flux, there's a paper by Forrest Moser last year. If you look at these things in terms of Poynting flux, there's an enhanced Poynting flux associated with the switchbacks, and that is really just this delta VR or delta VR that corresponds to the Alfvén wave eigenmode structure of the things. Okay, there seems to be some evidence of a preferred deflection direction. So you've got, let's say you've got the field pointing back towards the sun, which is what we see often at perihelion because we're south of the ecliptic, and the field switches back, to become positive radial. There's a question: does it switch back always in plus t or minus t, or is it equally distributed in plus t or minus t? And there seems to be some evidence. Tim has published some work suggesting that there's a preferred clock direction to the switchbacks, and that switchback and that clock direction is in plus T in the direction of the solar rotation. Okay, which is interesting. And this is some work that I'm doing right now, which suggests the same thing. This is for a large patch of switchbacks, large interval of switchbacks on the last encounter 9, when the magnetic field was inward, so it's negative polarity below the heliospheric current sheet. And what I've done is look at in 10-minute time intervals, I find the time when the field is maximal and minimal. The radial field is maximal and minimal. When it's minimal, it's essentially the solar field, the large scale 1/r² field. When it's maximal, that is the switchback. Okay, and then you can look at the transverse components that are associated with those interval by interval. And what you see is that, so the black in the right-hand side, this is in the plus or minus n direction. So this is out of the ecliptic. Black is the minimal field, which is centered on 0, basically. It's, it's centered in the ecliptic. It's expanding. It's a Parker field, Parker wind. And the red is the deflection during the switchbacks. The left-hand side is the tangential component, and so you see in the minimal field direction, it's displaced a few degrees from 180, and that is just the Parker spiral. You're just looking at the Parker spiral there. But the deflections, the switchbacks themselves, have a further displacement in that direction. So there seems to be some evidence that the switchbacks have a preferred direction of deflection, and this may be important in the sense of it may point to interchange reconnection below. It may have something to do with angular momentum transport. I think this could be an interesting angle of work. And the switchbacks are generally considered to be kind of long and thin. That is, actually a missing figure here. There it is. If you compute an aspect ratio, if you consider that you're slicing through these things and they have some cylindrical geometry, which is an assumption, you can compute an aspect ratio. And the aspect ratio is around 40 or so. So there tend to be a solar radius long in the direction of the radial flow, and much smaller, 40 times smaller across. So again, they're organized. They seem to be organized more or less by the magnetic field. Actually, this improves when you consider the Parker spiral direction, which is pretty small at solar probe altitudes, but it's finite. This improves. So it seems like we're dealing with something that's aligned with the magnetic field, has a large aspect ratio, and this spherical polarization sense. Where am I here? Okay, and they're getting weaker as we get closer to the sun. They're weaker in amplitude, and they're fewer in occurrence. So there's a paper by Forrest Moser, again, estimating switchback amplitudes as a function of altitude. And there's some interesting work by Sam Badman, who's a student in our group, showing the same thing in the context of measuring the open flux of the magnetic field, the solar magnetic field. So the switchbacks seem to be weaker and fewer in a sense as we get closer. And I think I'll come back to that, to what I think that means. Okay, so now I want to talk about the work that we just published. So this is a paper that's called a solar source of volcanic magnetic field switchbacks in situ remnants of magnetic funnels on supergranulation scales. So, and it's just was accepted last week to AppJ, so it's not out yet. It's on arXiv. And so what we've done is a case study of Encounter 6, of solar probe Encounter 6, which goes down to about 20 solar radii. And we've found that the switchbacks there, to cut to the chase, are organized in Carrington longitude. The switchback patches are organized in Carrington longitude by angular scales that are consistent with supergranulation, and that within those patches of switchbacks, the plasma is hotter and faster, has higher alpha particle abundance, which is a parameter that's set in at the source, right? This indicates a very low coronal origin, a photospheric origin, essentially, or chromospheric origin of these patches. And we also found evidence for very hot, what we think are alpha particles, 85 keV, super thermal tail to the solar wind distribution, which is very, very energetic. And I'll argue a little bit for a reconnection interpretation of this. That's not definitive, but it's my prejudice at this point. So Encounter 6 looks like this. This is an heliocentric inertial coordinate system. There's the spacecraft, there's the sun, there's the spacecraft. We're in Encounter for 2 weeks or so as we pass through perihelion. Unfortunately, Earth is over here. Stereo is over here. This is Solar Orbiter, which didn't have its remote sensing instruments on, and this is Bepi-Colombo, which doesn't pay attention to us. So the point is here that it occurred behind the limb. So there were no observations from Earth or stereo, magnetograms, UV AIA kind of images or anything like that at the actual encounter itself. And so we had to propagate existing measurements, earlier measurements and later measurements around to infer the photospheric magnetic field. And that was done by Olga Panasenko using a PFSS model. So she used I guess it's de Rosa flux propagation model on HMI data to have a magnetic field map at the encounter. So the magnetograms that went into this, the actual magnetograms that go into this are a little stale. They're a few days old, right? And they've been propagated around a flux propagation model. But using that model, she can compute a PFSS mapping, and that is this black solid line here is a heliospheric current sheet during our perihelion on encounter 6. And this figure, so what we have is this is Carrington longitude and latitude, and so the solar probe trajectory, like I showed you before, the spacecraft trajectory when mapped down to a source surface, which here is at 2.2 solar radii, the spacecraft comes in from the right-hand side here, and it swoops around like this and has its perihelion loop. And so the perihelion is here in the center of the loop, and then it swoops back out, and then it goes off like this. And so this is that loop that I showed you on those earlier orbit plots where we're looking down into the plane of the ecliptic. Now we're looking in longitude and latitude at the source surface. So again, the spacecraft comes in like this and swoops down, goes back out. And so we can constrain the location of the current sheet by looking at the polarity of the solar wind that we observe at the spacecraft. So you can, with these models, you can sort of tune the correspondence of the model to the ballistically propagated solar wind measurements at the spacecraft by moving up and down the source surface, which modifies the position of the current sheet at the spacecraft. And that's turned out to work pretty well for encounters where there's almost no solar activity, which is the case for encounter 6. When there are active regions on the disk, encounter 2, a little bit in encounter 3, PFSS doesn't work very well. That's maybe not a surprise. And there are some improvements that you can use WSA. There's some improvements we can do to this, but it generally, for quiet solar min wind, PFSS has worked pretty well to give good correspondence with the magnetic field and plasma observed at the spacecraft with the predictions at the source surface. Okay, so what I want to show you here that's interesting is okay, we're connected to this coronal hole. This is a coronal hole boundary down at minus 60 degrees. So this is where our magnetic connection goes. So what we do is we take the solar wind that we measure at the spacecraft and the magnetic field, and we propagate it back to the source surface. Okay, and then where it touches the source surface, you can map down to using PFSS, you can map down to the photosphere. Okay, so in here we're connected to this coronal hole boundary. So these little black contours that you see all over the place, these little bundles at the nodes on this plot are magnetic field flux concentrations at, I think it's at 1.02, so 14 megameters altitude above the photosphere. So this is, just above in the corona, just above the transition region. These are enhancements of magnetic field pressure, okay? And these are just simply the boundaries of the supergranulation cells. This is the network magnetic field. If you go up, another order of magnitude in altitude, it all gets washed out into closed and open field. So these are the supergranulation boundaries. And the point is, we know that these are there. The point is that the angular scale here is a few degrees. Okay, and that's well known too. But just to show you that our PFSS has network magnetic field bundles in it. So this is what we saw at Parker Solar Probe. And for those of you who aren't used to looking at these kinds of plots, I'll go through this slowly. First off, the top panel is a pitch angle distribution of electrons. So 0 degrees, 180 degrees. The field was mostly inward, so 180-degree flux is outward. Okay, so this red bar here is the straw. It's the heat flux of the solar wind, just enhanced. This is 314 eV, so enhanced superthermal electron flux flowing away from the sun. These little excursions from the unipolar flux here are proximity to the heliospheric current sheet. So as you get close to the heliospheric current sheet, there's a sheath of plasma around that, and that has a broader distribution of electron pitch angles in it, and so you see that a little bit. I'm going to steer clear of that because that confuses things. So we're going to look at this data from the right-hand side here, which is simple unipolar flux. So the field is radial below us. So these are the switchbacks. These bundles here of radial field reversal are the magnetic field switchbacks, and you see that they're now, as we get closer to the sun, they're more organized, right? I mean, there are clear modulations of the switchbacks in both the currents and in amplitude, right? So, the high amplitude switchbacks here are in the high occurrence intervals, essentially. Importantly, so this is plasma density. So there are a couple of density modulations associated with these patches of switchbacks, but not uniformly. These second few here don't have any pronounced density modulations, but the first two do. And importantly, there's a dip in the field magnitude. This is the modulus, the intensity of the magnetic field. There's a dip in the field magnitude as well associated with the switchbacks. And this is the velocity. So you can see the fuzzy edge of the velocity there is the switchback impulse. And you can see as well a modulation in the solar wind speed associated with these patches, with the bulk speed associated with these patches. This angular scale that we're looking at here, and this barred above the time is the Carrington longitude of the spacecraft. This angular scale is a few degrees, 3, 4, 5, 6 degrees or so in Carrington longitude, projected back down to the source surface. So that is the scale of the supergranulation structure of the network magnetic field structure. If we look more closely, and this is again, these next few plots are going to be kind of messy, but I'll walk through them slowly. This is again the magnetic field in the bottom. So you see the switchbacks. I've put these yellow bars on here to try to organize the patches of switchbacks. The next panel up is the alpha particle abundance. So this is the ratio of the alpha particle density to the total density, with the careful fit of the particle distribution functions and a nice true total density measurement. And what we see is that we have enhancements in here that are confined in some sense to the patches of switchbacks, and the abundance gets up to, in this case, 4%. Okay, so these are during solar minimum, which this is. These are fast wind like alpha abundances, right? Generally, the slow wind at solar minimum has a very low alpha abundance, like a fraction of a percent or so. And the fast wind has an abundance which is typically 4, 5, 6% or so. So this is fast like wind in these little bundles of switchbacks. The panel second from the top is the wind speed. There are several speeds here. There's the blue is the core proton speed, and there's a beam speed and an alpha particle speed on top of it. The alpha particle speed is in green, and the black speed here is the alphane speed. Okay, so you see that within these structures, the wind speed is enhanced. The alphane speed is depressed because the field is depressed. So they get to be sort of Mach 2 or so within the structures, but at the boundaries of the structures, the proton flow is almost Mach 1. It's not subalphanic, but it's close. So we're transiting through intervals that have enhanced velocity in them. And the top panel is the ESIS energetic particle. This is flux. And so you're seeing from 30 keV down to 85 keV enhancements in the flux within these last two funnels. I cut to the chase, I call them funnels. These two structures that have the highest speed in them. So that when the flow speed, the bulk speed is high, you see these tails, these energetic superthermal tails of particles emerging. Okay, let's talk more about that. So these are the distributions. These are fluxes of those last two intervals. So this is the proton flux in red, the alpha particle flux in black, and you see there's actually a beam structure here in the alpha particles. And then these are those ESIS, those three energies of ESIS measurements down here. And so the ESIS measurements are because of the essentially very low flux for them, these are very, very weak events. Because of the low flux and the low energy, they get into the regime where it's more difficult to separate mass. Okay, so there's some ambiguity here as to whether these are helium, alpha particles, doubly ionized helium, or probably oxygen, O5 plus, one of the two. So it's not quite clear. They kind of lie between the curves. I suggest here that they're alpha particles because of the putative, potential organization by the alpha velocity and by the spectrum. I mean, with your imagination, you can draw a line between that point and that point. And actually, these highest energy channels of the alpha particle measurement are potentially contain some proton flux too, so they could be a little steeper. So it seems to me, I would suggest that we're seeing up to 85 keV energetic alpha particles within these bundles of switchbacks and fast wind.
Stuart?
Yes.
Cindy, can I interrupt? Over how
Yes,
long a
please.
time period are those N4 and N5 distributions averaged?
They're averaged over the entire N4 and N5, so over the yellow bars.
Okay, thanks.
Yep. So one can do something more interesting. In fact, a thing to do would be to look at the temporal correlation between the alpha particle speed and and these individual spectra, for example. Okay. So this has a lot of junk on it too, repetitive, except that here I've computed the pressures, the magnetic field pressure and the plasma electron, proton, and alpha particle pressures. And the panel second from the bottom is the sum of those pressures. Okay, so the point is that the plasma is in pressure balance. Okay, so the way to view this then is that that at least over the transit time scale, the time that the spacecraft crosses it, which the structures, which is 6 hours or something, or a day maybe, these structures are static on the they're static in longitude as we drive through. So there's basically constant pressure across the whole interval. Okay, so that implies that it's spatial structure. It's spatial structure in longitude, latitude as we drive past it. Okay, there's more. This is getting into kinetics and stuff, but there are kind of enhanced anisotropies. Actually, I'm going to skip this because I'm running out of time otherwise. Let me show you this. So these are breakdowns of the alpha particle perpendicular and parallel temperature, proton beam perpendicular parallel, proton core perpendicular parallel, and electron core perpendicular and parallel within the structures, which is the hashed data, and outside of the structures, which is the beige colored histograms. So you see that for the alphas and protons, both beams and cores, the plasma is hotter in these intervals than it is outside. For the electrons, you can't really see it here. I'll show you on the next slide, but the electron core temperature is actually depressed within the structures. Okay, so here I've got all of them averaged together, so it's kind of smeared out. On the next slide, you'll see that. But that's kind of consistent with fast wind too, right? We know that in the fast wind, the alpha particle abundance is enhanced, the electron temperature is depressed a little bit, and both of those parameters are thought to be frozen in essentially at the energization down at the chromosphere, right? The first ionization potential of hydrogen or of helium is whatever it is, 54 eV or something like that. It's too high to modify beyond the transition region. And these values actually kind of fit nicely. I don't know if you can see this plot. This is from a paper by David Stansby, who used Helios data to compute a proton and alpha perpendicular and parallel temperatures as a function of altitude. And if you take our data and extrapolate it inward from David's paper, we're kind of in the same regime. It's consistent. If you look at ratios, normalize everything in the top panel to the proton core temperature, what you see is that the alpha particles are very hot. Okay, so the alpha particle to proton core temperature is much more than mass proportional, right? Mass proportional would be 4. It peaks here at 8, and we have counts out to 20, a factor of 20. Here you can see the electron core temperature is depressed over the proton core temperature, and this is the beam temperature. These are the anisotropies, and so you see that everything is pretty generally isotropic except for the core proton distribution. As I said earlier, the core protons are hotter in the perpendicular direction than in the parallel direction in general.
Stuart, you have 5 more minutes.
5 more minutes. Oh boy.
Yep.
Okay, that's fine. Okay, so what we've done is map all this stuff down. We take the data, take the measured velocity at the spacecraft, and we can map that down to the source surface using a ballistic propagation, the old Nolte and Roloff idea. And so we can kind of map this out in Carrington longitude at the source surface instead of looking at the time temporal variations. And so what we see are steepened. This is the velocity structure here. The blue is the minimum. We see these steepened structures that look like they have a steep edge at the photosphere, and so the more or less sinusoidal structure that you see at the spacecraft is a result of time of flight. And so we have structures that are steepened. The angular scales are supergranulation scales. The switchbacks tend to be organized in the leading edge of these things. These are the red here is the switchback amplitude. Up here, this is the magnetic field switchback amplitude. They're organized at the leading edge, sort of a 1 degree edge here that also includes the transition of the density or the temperature. And interestingly, in this panel here, this is the parallel proton temperature, includes that enhanced parallel heating. So the organization down at the photosphere, at the source surface is supergranular scales with a leading edge that has hotter, faster plasma in it, and the switchbacks seem to be associated with that. This is the same plot put into polar coordinates. So what I would suggest is that we're seeing outflows from magnetic funnels. The depression of the magnetic field at the center of it is simply a result of the overexpansion at very low altitudes. The radial field component goes like 1 over r squared, 1 over the area of a flux tube, and the tangential components go like 1 over r of a flux tube. So the center of the funnel, in some sense, has overexpanded, has lost more field intensity due to this overexpansion. So that depression is indication of a funnel-like structure below us. We know that there's type 2 spicules and jets and plumes, for example, that are organized by network magnetic field and by these funnel structures. And I'm suggesting here that that's the source of at least some of the switchbacks that we see. The switchback patches are organized by these structures. This is a cartoon from our paper that you can look up. Same thing. Unipolar fields here that emerge as funnels. This is a 2D potential model and produce these structures. Since I'm going quickly here, I want to show you this. This is a comparison of our data in red to data at Solar Orbiter at 200 solar radii, which was on the same Carrington longitude. So it's seeing the same solar wind much later. And the structure is gone. This is the velocity structure in the top. The structure has evolved away by 200 solar radii. The magnetic field is turbulent. Okay, it's got some compressibility to it. It's got some organization in it, but there's not a clear mapping of what we saw when we saw that same plasma. A couple days earlier, it had all this structure in it, and that structure has evolved away, presumably just by turbulent evolution, parametric instability, etc. Except for the alpha particles. There's some remnant, potentially some remnant blue of the alpha particle abundance modulations, not 1-to-1, but there's some structure and some enhanced, 4% values on those same parcels of plasma, which is maybe not surprising. I mean, the alpha particles are, it's difficult to modify the density of the alpha particles as they propagate out. You can modify the flow speed by instabilities, but the density is more difficult. So those are our main observations. Switchbacks are modulated on supergranulation angular scales. The photospheric field, of course, has similar scales. They're pressure balanced at 20 solar radii. These patches, these funnel structures contain faster, hotter wind, higher alpha abundance, lower Stral energy, all things that are frozen in at the source, we think. There are superthermal particles to 85, alpha particles to 85 keV. By the way, that 85 keV corresponds to an alphane wave energy, you know, 1/2 m alpha times v alphane squared at the chromosphere, essentially. So it's consistent with a process energizing alpha particles to the alphane speed at that altitude. And it's mostly evolved away by 200 solar radii. So why haven't we seen this before? Okay, I would say, when I wrote this slide, I would say that now that we know what to look for, we see it. I have some slides on Encounter 9. I won't have time for that maybe, but that's okay. And I want to point out this paper by Naïs Farget, which is in press, actually in the journal now. And what Naïs did was look at the earlier encounters and look at just the magnetic field and map it onto the photosphere in angular concentration, in both, actually taking both longitude and latitude into account. And then she did wavelet transforms of the fluctuations organized by Carrington angles, and found again a concentration associated with the supergranulation scale. So there's an independent, more statistical analysis using just the magnetic field, suggesting that the supergranulation scale is the organizational angle for the patches of switchbacks. And that's the rest of the stuff I have is on Encounter 9. So if I'm out of time, I'll save that for another talk.
Okay, great. Thank you.
Sure.
Now we are open for questions and discussion. We have quite a few people, so I propose that those who want to ask raise their hands to make a queue. Questions or comments? Okay, Jim Klimchuk.
Hey, Stuart, this is very neat.
Hi.
I didn't quite follow, however, what you said about the overexpansion of the flux at the core of the funnel. I mean, I would have thought that if the field strength down at the base of the funnel in the photosphere is more or less uniform, then the field strength higher up should be more or less uniform, and so the expansion should also be uniform.
Well, okay. So, I mean, I think the idea, I'm not an expert on the photosphere, but I think the idea is that you have pressure balance in the structure, and so the magnetic field falls off faster. Essentially, the magnetic field pressure falls off faster than the plasma pressure does, because it's a multipole field. And so as it does, the plasma pressure wins out and makes the funnel expand, makes the structure expand above some altitude, 10 megameters maybe, and then if you think of just a flux tube, a simple flux tube, I mean, we like to think of expansion as being spherically symmetric, right? In that case, the field or the density or whatever falls off like 1/r², because there's no flux tangential, because it's a sphere. If you look at just a flux tube and think about a flux tube and think about an element of a flux tube, the radial that's expanding into a sphere, the surface that's perpendicular to the radial has an area of πr², right? And so that gives you the 1/r² expansion. But the surface that's the band around the side of it expands like 2πr, okay? And so that has a 1/r expansion associated with it. Actually, that's not exactly true, because if there's acceleration, that band will expand radially as well. But assuming constant acceleration, that little band of flux has a 1/r fall off with altitude. And so if you just consider that little, that slice through a flux tube as it expands outward, you get that the field in the center, which is expanded radially more than field that has a component that exits the flux tube, that falls off faster than the flux at the edge. And actually, this is really just the basis of the expanding box simulation business. I mean, they essentially use that principle there too. So that's our argument. And
Okay.
you know what? You're not the only one who needed some convincing.
Okay. I'm not I'm yet convinced. We should talk about it later, but let me just make this point. I think for these funnels, most of the expansion takes place in the low beta region of the extreme lower corona. So it's all happening low down, but in the very low beta region.
Yep.
Okay. All right. Well, let's talk more later. Thanks.
Let me say one more thing about that. So what we're seeing out at Parker Solar Probe is near the ecliptic plane, right? So this plasma, which started at 60 degrees south, right, has also had to come has had to overexpand well beyond that low coronal funnel expansion. So let's say there's some funnel expansion that starts to fill space down in the low corona, in the coronal hole. that coronal hole itself has had to overexpand as well to get to the ecliptic plane. And so the fact that we're seeing very low speeds, a few hundred kilometers per second, what we're seeing is fast wind, I think. The structure that you would call fast wind if you saw it, if the spacecraft itself were at 60 degrees latitude, but it has a slow bulk speed because of the secondary overexpansion, the Wang-Scheele kind of overexpansion.
Yeah, we have to go to next
Okay. Yep.
question. Lakshmi, please go ahead.
Thank you. Stuart, this is a great talk. Could you comment on the spatial interrelation between switchbacks at the source, that means at the Parker Solar Probe region? When you see a bunch of switchbacks or the order of one fluctuations in the magnetic field,
Yeah.
Are we crossing multiple switchbacks or is it just one switchback? If we cross multiple switchbacks, how they interact with each other?
Well, that's a good question. I think we're crossing. Let me go back to my conclusions here. I don't want to make Nais responsible for anything I say. So I think what we're seeing is we're seeing patches, and I actually have a slide. Let me cheat. Let me go to Encounter 9. Here's what we're seeing. So this is Encounter 9 data, and so we're looking down now into the XY plane, and I've put this. This is basically the red bundles here are patches of switchbacks. Okay, and I put them onto the trajectory of the spacecraft, and these dashed lines here are 5-degree lines. So what we see as we get close is these bundles of switchbacks. Okay, so there are multiple switchbacks within each bundle. Hundreds. Okay, and then green quiet intervals between, and they look in a time series. They look like the patches are shorter when we're closer to the sun than when we're further from the sun, and that's because of the orbit. Okay, so we're cutting across longitude at perihelion, so that what you have is a flux tube here that's filled with switchbacks, flux tube here, a flux tube here, and we're crossing them. When we're out like this, far from the sun, here's a flux tube, and we're driving along the flux tube. So we see a long patch of switchbacks in time. How they interact with each other, I don't know. I mean, I guess eventually, it's strong nonlinear Alfvén waves essentially, and I guess eventually they break up by parametric decay, I would guess, which is universal, and become the turbulence. I don't think they're plowing into each other necessarily or anything. I think they're just becoming. My instinct is that they just evolve nonlinearly and become Alfvénic turbulence as we get further out. But I don't know the answer.
Great, thanks.
Okay, thanks. Kostas.
Thank you, Gregory. Thank you, Stuart, for a very informative and interesting talk. My question is about the supergranular scale that you mentioned.
Yes.
You're quite far from the photosphere, right?
Yes.
You
20
would expect from the point of view of field lines, you wouldn't expect the magnetic field associated with the supergranulation to go that far. This is one point. And the other point is that you don't see any signs of the chronospheric network, which is associated to the supergranulation in the low corona. So how can you explain that you see signs well further away than the low corona?
The picture I have is that these funnel structures are on the boundaries of of the supergranulation cells, and they open up within coronal holes. They open up, and the flow is emerging from them. Okay, and so as you get to some higher altitude, that's a space filling effect. But and eventually, it's within a coronal hole. So all this stuff emerges from the through the source surface out to create the solar wind. And that structure is just frozen in, that velocity structure and that alpha particle abundance, for example, was set after everything became space filling and emerges.
I'm willing to accept this picture, but then you should still see something in the low corona, and you don't. You see no signs of supergranulation, let's say chromospheric network in the low corona. It's gone.
Yeah, that's probably right. Yeah, I know. I think that's right. I mean, by the time you get to 30, 40 megameters or so, all this stuff it must have become space filling.
Stuart, can I comment? It's Olga.
Hi, Olga. Yes.
We do have pattern relative to supergranulation on photosphere in the corona. It's called the coronal cells. And
Yes.
similar pattern you can find all the way from the photosphere to on chromosphere fibrils and higher the supergranule cells as photosphere and chromosphere fibrils and coronal cells, they all found to be linked to supergranule scale and origins. So you can check Yimin one recent papers, not recent, like a few years ago. He has 2 or 3 papers about it.
Okay,
So-
but let me go back to the queue of questions. Why jumped? Please unmute yourself.
Okay, great, thanks. Stuart, this is John Wygant. Could we go back to the slide where you showed the steepened structures that are on the supergranulation scales that have
This one, like this.
yeah, and so here's what I was wondering about. There's a steepened side, and then there's the gradual side as you move out the other end. So
Yep.
what is the conceptual picture here if these are spatial structures? I mean, if we reverse the trajectory of the spacecraft, would the leading edge be not an edge, but a ramp, and the trailing edge would be the steepened side?
Okay, here's my conceptual picture, John. I think that's why I made this figure. So this is a potential field. This is the Hackenberg and Mann 2D potential field of there's a unipolar field here. There's a dipole, and I put a little shear on here. Okay.
Uh-huh.
We think that the photosphere and there's a little differential rotation between the photosphere and the corona. So I think putting some, or just being near the edge of a coronal hole, it's plausible to put some shear on here. So that introduces a kind of asymmetry to the things. Right?
I see. Okay.
Okay. So and interestingly, there are no bipoles in here. There are no granulation fields or anything. But you actually get this kind of cusp geometry, anti-parallel cusp geometry in 2D. Very simple, naturally from this kind of thing too.
I see.
So for me, that's the conceptual picture.
I got it. Okay, great. Thanks.
Can I comment on this? This is Jim. So when we saw that, I mean, my interpretation is that as he's going into the part where you have these large fluctuations, he's entering into the reconnection exhaust for the interchange reconnection. And as they die out, he's going deeper into the exhaust. And when you go deeper into the exhaust, you're seeing lower flow speeds because it's stuff that happened earlier in time. And so that's, to me, why you get this asymmetry.
I mean, I agree with the asymmetry, the leading edge asymmetry being associated with the reconnection outflow personally, but I know, Jim, we have some colleagues who think there are other explanations too.
Okay, next question.
So in principle, if you reverse the trajectory on some other encounter and you had a slightly different geometric configuration of these sources at the bottom, then you could have the trailing edge be the steep one.
Essentially so, yep.
Yeah.
All right, let's go to next question. Django, please unmute yourself and go ahead.
Okay, thanks.
In the talk, you mentioned that within one switchback packet, there are many individual switchbacks, and someone examined how they distribute to find like a power distribution over the duration time.
Yeah, that's right. That's right. If you look at so there's this classic now paper by Thierry de Doctevit where he looked at the deflection angle from the Parker spiral direction, and computed the residency time of that angle, and that's a power law essentially. So the switchbacks themselves there's no particular time scale associated with them, and to me that's an indication of an intermittent process at the source, just injecting alphanic fluctuations.
Oh, I see. Well, I thought that if this is solar origin, we should be able to similar distribution in the base of the switchback field lines.
I mean, so no one has succeeded yet in doing anything correlative between what we see at the spacecraft and anything at the sun. There's some efforts that way. And I think Encounter 11, there's going to be a big campaign. There are a lot of assets looking directly at the perihelion of Encounter 11. So we may be able to answer your question after that.
Okay, Thank you.
We're almost out of time already. We have a couple more questions, so please keep those really quick. Chile, please unmute yourself.
Thank you. Thanks for the nice talk.
Mhm.
So I'm not sure if I missed this. In the earlier parts of your talk, you mentioned the switchback is weaker and fewer closer to the sun.
Yes,
And
yes.
Did you comment on that, whether this is how you make this consistent with the origin near the sun?
I think this is just a result of WKB essentially. I mean, we would expect by conservation of wave action that there's a radial profile to the amplitude, the conserved amplitude of the fluctuations. But I think that I think we're seeing clear organization by supergranulation, which tells me that there's a injection source at the sun, but there's clearly radial evolution as well. And that radial evolution is, to 0th order is WKB plus expansion plus conservation of field magnitude. But it's a good question. There's definitely more work to do on that.
Okay, so last question from Hugh.
Right, thanks, Stuart. That's great stuff.
Hey,
My
Hugh.
question just is that you're seeing these excess Poynting fluxes, and they have to come from somewhere. So where are they coming from? And it would be cowardly to say reconnection because there's something more fundamental that would have to drive them.
I think the Poynting flux, Hugh, is related to the spherical polarization, to the arc polarization. It's
Yeah,
just if you take this arc polarized structure and consider that it's a plane wave.
Yeah, but where does it come from? What's its origin? What's the physics at the photosphere that does it?
It's the Alfvén wave. It's the velocity response to the Alfvén wave. I mean, in the kind of analysis that's been done anyway, there's the field goes one way and the velocity goes another way, and you end up with a velocity.
I understand that, but I'm wondering about where does the wave come from?
Oh, good question. I mean, right. It could be It could be the result of an impulsive source in a reconnection jet, for example. They could just be foot point. It could be a foot point motion in these structures that launches Alfvén waves. Maybe it's the tail of synchrotron wave or something.
P modes. You have to have some driver flows to make the reconnection happen if you want to have reconnection.
That's right. You'd have to. Yeah. Don't know.
Okay.
Okay, thanks. Let me thank the speaker and participants again, and please join us in November for the next event. Thank you very much. Bye.